So, in this video, we're going to discuss one of the most important theorems in mathematics. Now, some of you all may have been familiar with this, some of you all may have heard about this, some of you all this may be new to you, but it's called Pythagoras' theorem. So the Pythagorean theorem, Pytho. Pretty sure I spelled that incorrectly. Pi, Py, ta, Pythagoras' theorem. Now, I may have spelled this incorrectly, but it's the math we considered. We consider in here. So Pythagoras' theorem. It states for a right angle triangle. Well, we should be familiar that the longest side is called the hypotenuse. It's directly opposite the 90-degree angle, and here we could call this B and we could call this A. And the hypotenuse in context of the Pythagorean theorem, Pythagoras' theorem, you get variations of the theorem itself, or the pronunciations. You let the hypotenuse be C. This is what it says. C squared is equals to A squared plus B squared. This is the Pythagorean theorem. Now, this seems simple, but the implications of this and the usages of this are profound, not only in mathematics and many fields in mathematics, but also physics and many fields in physics. Now, I know this because I am a mathematician and also a physicist. I've yet to start to make physics videos, but I decided to work on the maths first and get to the physics because my true love was always physics. I get to love maths later in life, but my true love was always physics. So, this is the Pythagorean theorem. So, looking at an example of this, simple example, we have, if here is 3 and here is 4, what is the hypotenuse? Well, the hypotenuse in the context of the theorem is C squared. The C is labeled as C, so we say C squared is equals to A squared plus B squared. And we say C is equals to the square root. To get rid of the square on this side, you take the root of everything on this side of 3 squared plus 4 squared. C is equal to the square root of 9 plus 16. I believe that is equals to the square root of 25, which is 5. So this length here, the hypotenuse is 5. cm, meters, kilometers. When I'm introducing and talking about examples, like, I don't usually include units because they could give you questions with any units. It's just to generalize the concept. And you could do the same thing if you have the hypotenuse on this side. You just rearrange the formula and basic algebra. But that's not what I want to look at. The use of the Pythagorean theorem. I want to look at a deeper understanding of where this comes from. So let me just clear this. So everybody by now know I'm using Paint to do this. It's one of the best graphical interface software. I don't care what anybody says, Microsoft know what they're doing. Okay, so let's consider a right angle triangle, right? So when we think of a triangle, we could say, well, it's a shape with three lines. But Pythagoras had the insight to think about the triangle as being where defined in terms of three squares. I'll try to draw this as best as I can. Let me change the color for this. Yeah, let me change the color for that. Let me try to draw this next square to the bottom. Now this is some delicate. So we have a next square there. Hey, Rastafari. That was unintentional. And well, the other square, I would have to draw this a bit different because of the limitations. I'm pretty sure I could orientate it, but I don't know how, so yeah, that supposed to be a square, but kind of run out of space on top, so yeah. So he thought about the triangle in the context of three squares. You see three squares? First square, second square, third square. And when you basically like when you could define the triangle as the contact points of three squares, like where the vertices of three squares meet, like over here, over here, over here, and these three things are squares, and inside we have the triangle. Now that was overkill, but that is what allowed him to say, okay, well, the area of the square, if this was square, let me call the square C, is C squared, because C by C, the area of the square, if this was square B, is B squared, because if here was B, if here was B, and the length of the triangle here is B, here would have been C. Don't know if you all seeing what I'm trying to get at here. And here would have been E, a square with length E. I just keep in the convention of the traditional notation of the Pythagorean theorem. It could be any other variables, but A, B, and C is the convention. And well, the area of the square is A squared, side by side. And he realized that the area of this square is equals to the area of the other two squares. And because there was a triangle that formed when the edges of, the vertices of the squares were met, it's like a next way of defining a triangle, like in the context of three squares. For those of you who understand that, I was trying to keep it simple, but I had to kind of up the language usage to get the point across here. So you could think of a triangle like being three lines or defined in terms of three squares. And because of this, thinking about it being defined in terms of three squares, it allows you to get through, like as I showed in the previous example, to do calculations like that to find out useful information about right angle triangles. Now, right angle triangles are very, very important. I would say this again in so many fields in mathematics and in physics. Like, it's so funny. Like, it's only when a student go on to tertiary level they will realize, wait, now, so much times we have to be using the Pythagorean theorem, and it will amaze you, I'm sure. Now, that's it. Next time we will talk about the trig ratios.